This presentation is entitled Project Management. In this presentation, we demonstrate clever use of Divine Inspiration's TCSQL technology in support of project management. In this presentation, you'll see powerful query capabilities on a project plan that you wouldn't normally be able to do in most project management systems today.
Project management. The application mentioned on the previous slide is founded by a powerful technology called TCSQL, which features the ability to maintain graphs, particularly with a powerful capability called transitive closure, features the notion of something called a soft schema. We're going to start by doing a little graph theory here. In front of us are two graphs, a family tree and a graph of bus routes. Some of the components of a graph consist of the following: the notion of something called nodes. In this family tree graph, the nodes happen to be the names of people here. A second component of graphs are these things called connections here, or edges. And they happen to be the arrows we see between nodes here. Sometimes in graphs, you have a semantic relationship associated with these arrows. In this family tree graph, we have a father of relationship, and we have a mother of relationship. Sometimes with graphs, you have scalar values associated with the connections. In this bus routes example, the scalar value represents a cost of going from one city to another. The object-oriented paradigm can be represented as a graph problem. So here we have a class here called class 1, which has properties A, B, and C, and a has a relationship between the class definition and its associated properties. We also have another class here called class 1.1 with properties D and E. And we see a relationship here between these two nodes, an is-a relationship, meaning that class 1.1 is a specialization of class 1. Now let's look at a graph here. Let's look at what happens if we want to instantiate class 1.1. Let's look at the equivalent object graph. In this case, it would look like the following. Assuming we want to instantiate class 1.1 and we're going to call that object 1, what happens is the following. We first want to instantiate properties D and E, and then we want to look at this inheritance is-a link here to inherit properties A, B, and C, which is what you see down here. Okay, now let's look at the relational tables needed to support this paradigm here. So we have the notion of a class table here, which represents the nodes of our class graph here. It's basically a name-value pair here, and we have a type column here, and legal type values. This represents basic class types here. We have a class connection table of parent-child nodes here, and a connection type here. In this case, it's going to be either has-a or is-a. And then we have a transitive closure table representing the transitive closure of this class graph. And assume for a minute that this transitive closure table is automatically populated and managed whenever nodes or connections are added or deleted in this class graph. Let's look at the tables needed to support our object graph here. We have a table called object, which represents the nodes of our object graph here. Again, it is basically a name-value pair with a class column here representing the kind of class that we're instantiating here, including the class properties. We also have an object connection table here, which represents the connections of our object graph. So it's a parent-child pair, again with connection type. And we have a transitive closure table associated with our object graph. And assume here also that this transitive closure table is maintained automatically whenever nodes or connections are added or deleted in our object graph here. So this whole paradigm here I'm describing here with these 6 relational database tables is something known as a soft schema. With this soft scheme model, let's look at an example of instantiating a class instance here. So we have a class graph here, and all the data in this graph can be represented with 2 tables here. So we have a class table representing all of the nodes of this graph. we have a class connection table showing all of the connections here. Now I didn't bother showing all of them. I just showed a few of the rows here. Okay, now let's look at what happens when we want to instantiate this particular node here, a boy. What we're going to do is instantiate this boy. We're going to call this instantiation Andy here. And what is going to happen behind the scenes is TCSQL is going to figure out all of the particular properties that need to be inherited here, and it will populate appropriate object and object connection tables here. And these two tables will represent an object graph that looks like the following here. Notice here that I've introduced a new kind of relationship, a has-not relationship. TCSQL supports the ability to do inheritance override here. Now, if you were to implement this in an object-oriented language such as C# or Java, this is the object graph equivalent what you would get here. Now, the real power and beauty here is I did this directly in a relational database using standard SQL. The use of TCSQL provides the ability to develop rather sophisticated applications. For the application featured in this presentation, we're going to use a schema consisting of the following. A couple conventional relational tables here, one for time card records and one for personnel records, and we'll use the notion of a soft schema to represent the data in graphs. Let's look at another query type example. We have a graph here representing an object breakdown structure here. So we have an organization broken down into various departments here. We see a legend here, so we see the relationship between nodes here is OBS, organization breakdown structure. In support of this graph, we have two tables here, a transitive closure table of the graph, and a table representing a collection of people associated with each department number here. We have another graph here called a work breakdown structure class graph here. So this is representing a template for a project plan. So projects are broken down into one or more features. Features are broken down into hardware and software units. And we see a feature has a property here called customer. We see a small feature and large feature are both specializations of this general thing called a feature. Small feature and large feature each have their own properties here. We see a feature also is broken down into hardware and software units. Those have properties of firmware and NCSL respectively. NCSL stands for non-commented source lines. And we see NCSL is a special instance, a special name for a more general term called lines. We have a couple tables associated with this graph, a class table representing the nodes here and a transitive closure table of this graph. And we have another table here, a WBS instance graph, meaning that this represents an instance of this class graph here. We have a couple projects here, P1 and P2, broken down into small features and large features, broken down into software and hardware units. We have a number of properties associated with these entities down here. Okay, we have a couple of relational tables associated with this graph. We have an object table representing the nodes of this graph and a transitive closure table representing the transitive closure of this particular graph here. And the query we want to perform is the following. Imagine you're the manager of a department up here, organization 553. And what you want to know is you want to know all of the features your people worked on and the total number of lines they contributed for each of those features here. Now, if you think about this, this is a very complex kind of example. It requires the traversal of all three of these graphs here, the object instance graph, the class graph, and the work breakdown structure instance graph here. It would be something very, very complicated. Rather than show you a complex select statement here, doing a join of the associated tables with each of these graphs here, what I'm going to show you instead is a select statement that utilizes a view definition that hides all of the detail here. And so what we see is select star from organization contributions, where the organization name is 553, where something called a superclass is this notion of a feature, and superclass property is lines. We want to know how many lines for each feature for the people working in organization 553. Now, the interesting thing about this query is the following. Let's say tomorrow that someone decides to change this class definition here, decides to introduce something called a very large feature. What would we have to do to this query to incorporate the notion of a very large feature? The answer is nothing. This query does not need to change at all. What if tomorrow someone decided that, well, in terms of lines, we also want to call firmware a kind of lines also? What do we need to do to this query to incorporate that kind of logic? And the answer is absolutely nothing. The only thing we need to do is, in fact, put a connection between the notion of firmware and lines to indicate that firmware is a kind of lines here. This type of query is what's called a polymorphic query. And the beauty of this kind of query is it allows you to make changes here and never have to make modifications to the original queries at all. One of the classical activities associated with managing a project is the derivation of what is called critical path. It's a collection of tasks such that if any task in this collection misses its end date, the end date for the overall project is pushed out here. Now, there are a lot of classical procedural algorithms for deriving critical path. What I'm going to demonstrate here is the ability to derive critical path declaratively using TCSQL's transitive closure. So what we see here is a select statement, select task from critical path where destination equal TN15. Critical path is a view, and I will forego looking at the details of that view definition, but suffice it to say what is returned is the following. And it's an ordered list of tasks which comprise the critical path here. So this is an example of something called a path query. So why is this valuable? Well, what I've demonstrated is the ability to derive an actual path from transitive closure records. Now understand, transitive closure records only have the endpoints of a path. And still, only having the endpoints, it is possible to derive an actual path. Secondly, I've demonstrated the ability to create a declarative solution to a problem whose solutions are typically procedural.